Good evening, students. So today I'll take this a different kind of proof for Fermat's little theorem, which states that if p is a prime number, then for any integer a, the number a raised to p minus a is an integer multiple of p, which means p divides a raised to p minus a. As a prerequisite to prove this, I'll take few assumptions, and I hope you are all aware of it. Number one, you know this particular expression, this particular symbol, which is binomial coefficient, which is basically n factorial upon a factorial. Let me make it r because we had already taken a in the question. So if n c r, so this is basically n factorial, n choose r factorial, n minus r factorial, and this is an integer, the first assumption. Second, I take this coefficient n choose a1 arrange a2 a3 dot ak is basically, let me place n somewhere in between, it looks nicer, is basically n factorial upon a1 factorial, a2 factorial, and so on, ak factorial, and is also an integer because this represents number of ways of arranging n objects of which a1 are alike of one kind, A2 are alike of other kind. This is basically dealt in initial combinatorics in all classes of high school. Besides, I also take an assumption that n choose r is divisible by n if n is prime and r is not equal to 0 or n. Why do I take this assumption? Simply because at the very first place we have said that n choose r is an integer. Now if this is an integer, so I would say that 1 into 2 into 3 up to n whole divided by 1 into 2 into 3 up to r and 1 into 2 into 3 up to n minus r was an integer, which means that the entire denominator cancels off the numerator. But n is prime. So n cannot be cancelled with any two numbers multiplying together and forming n. And there is no n in the denominator because the only two ways by which n could have been there, we have ignored them, we have discarded them. So that means whatever denominator gets cancelled with the numerator would be with the rest of the numbers, as in this way. So this comes out to be some lambda times n, and hence NCR or n choose r is divisible by n if n is prime. Much in the same way for this other expression, n arrange a1 a2 a3 ak is also divisible by n if n is prime and none of the ai is either 0 or n. So that means rather than calling not equal to, I have given them all they don't belong to this set. The same reason, this is an integer representing the number of ways of arranging n objects of which a1 are alike of one kind, a2 are alike of another kind, and so on. And in the numerator, n factorial, if I write it something like, let me create some space here. Yeah. So if I were to put it this way, that the number of arrangements is essentially n factorial, a1 factorial, a2 factorial, up to ak factorial. So none of these a1, a2 factorials will have either n or 0 because we have restricted that, and still this is going to cancel because it is an integer number of ways of arranging. So even this comes out to be some n times lambda dash. So that means both of these coefficients are divisible by n if n is prime and we restrict coming n in the denominator. Now I'll take out some space, erase this thing, keeping the definition of the statement of Fermat's theorem intact. So what I'll do is I'll take an expansion, and this will establish the Fermat's little theorem in one line. I take somewhat like b1 plus b2 plus dot 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 bk raised to n, and if I expand this, so as an expansion, as a formula, I get summation b1 raised to a1 into b2 raised to a2 dot 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 bk raised to ak with a coefficient, and that coefficient is nothing else n arrange a1 a2 dot 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 ak, subject to condition a1 plus a2 plus dot 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 ak is equal to n. Now if I look at this expansion, this basically is an identity. So this is going to be true for all b1, b2, b3, bk irrespective of the values of bi. So plug all bi's is equal to 1. In the left hand side you get k raised to n. In the right hand side you get lot many terms where if n is prime, other than those terms where these ai's basically are n or 0, that means if one of the ai is n and the rest all are 0, only in that case this basically would be not divisible by n. Otherwise, as we said earlier, if n is prime, every other term would be divisible by n. How many such terms occur? The answer is every time there is a ai which goes n, this entire value becomes 1. Then a2 becomes 1, this entire value becomes 1, and so on up to k times plus more terms. And when I talk about more terms, so I'm very clear that all these other terms are essentially divisible by n if n is prime, by the result that we established or that we took at the initial stage in this proof. So by that, if I look, this entire expression is divisible by n if n is prime, and we have removed those cases, taken these cases which are basically 1. So if I put it on the left, take them on the left hand side, I'm left with k raised to n minus k is equal to this, something which is divisible by n if n is prime. So this establishes or proves my result. I'll take later k as a and n as b, and the result is done. Thank you.